All right, let's look at the review for the test two. We plan to have the Friday, and there are a couple important concepts and the technique we really want to review, and we are going to do this in backward order. So we are going to list the important concept and technique, and for some of them, we're going to have example, but not all of them. Okay, so the first one we want to emphasize is that how do we compute double integral? All right, so the definite integral, the double integral, what we are referring to is a definite integral, and we do want to emphasize there are three factors. This is domain of integration, this is the integrand, and this is the differential of area. And for each of those, we notice the most important thing for us to evaluate the double integral is to represent R as either type 1 or uh, type 2 region. Okay, and then set up the iterated integral. So this is what we need to do. And we always have two ways because we have dx and dy, right? So first of all, we note differential of area could be either dx times dy or dy times dx. So the double integral could be written as in this two different order of the iterated integral, as we always say. And we can treat this as a type 1 region by integrating about the y variable first as the interior integral. Okay, but for the type 2 region, it will be the last one to integrate. And obviously here, uh, for the type 2 region, or our y variable will be fixed or bounded between constants. And in the type 1 region, on the other hand, x variable is for the exterior integral, and x variable will be having the constant bounds. Okay, and for the uh, type 2 region, we're integrating about x variable first, and so here let's focusing on the type 1 region. And when we do integrate the interior integral first, we have to do what? We have to do the integral for the y from some value to another one. And if, for example, so how about we do we discuss the case, either case first. So if R is indeed a rectangle region, okay, then the two iterated integral will be relatively easy to write because the lower bound for x and y will be constant and the same for the upper bound. So the lower bound for y will be c and the upper bound will be d. Okay, and for the lower bound for x will be a and the upper bound will be b. Okay, so this is the most of the simple case, which is the domain integration is indeed just a rectangle, like given here. All right, what if things are a little bit different? If we have type 1 region like this, okay, obviously the x equals a, this is x equals b, but we also have the y is given by a lower curve. So this is the y sub b of x, and then this is the y sub t of x. Okay, we are going to see the y will be bounded between those two curves. And then in this case, how do we write the iterated integral? So this is r or d, if you choose to use different letter. Okay, if this is the type 1 region, and then we're going to integrate about the y variable first in as the interior integral, and the x variable for the exterior integral, and obviously x value is chosen from a to b so that the limits for the exterior integral will be constants. But then for the interior variable y, the lower limit is determined by where this y sub b of x, and the upper limit will be given by y sub t of x. Okay, and on the other hand, if we're looking at the type 1, so this is type 1 region, and for the type 2 region, we treat this region as this, and then we'll have this y will be bounded, y will be bounded by so y equals d and y equals c. Y will be bounded by those two constants, but x will be depending on something that is given here. So this is x left of y, because at different height of y, the x coordinate will be different. And on the right, we have x sub r of y. And then this double integral will be written in this iterated integral way. And we're integrating about the x variable as the interior integral. And we're going to integrate a y variable for the exterior integral. And here we know y is running from c to d. All right. And then the x is going from the left to the right. Okay. So with those really abstract notation, we deal with the most simple case, which is a rectangle, and the general case, which are treated in either type 1 or type 2. You got to review the classic examples and to try to do those homework again, and then try to get a sense at what you, the homework is, there is set of homework, you can work on those. There are actually a problem about setting up the double integral and triple integral, I mean iterated integral. Okay, so this is the first topic, and the most important part is this, and those three, right? And for the second item is optimization. Okay, and the optimization have a couple things. The first one is so-called the critical point. The way of finding critical point is to set all the partial derivative to 0 and solve the equation altogether. Okay. Okay, and the second one is the so-called second derivative test for classifying critical points, either local max, local min, or saddle, or cannot be determined. And to use the second derivative test, there is one of the important feature of formula we need to remember, which is the so-called the discriminant, all right? And we can only tell about the local max, local min when this discriminant d is bigger than 0. And so, okay. And how about the others? So in this optimization, the third item will be the absolute maximum value and a minimum value. How do we get them, right? There's a fixed procedure. The procedure, we can list the first procedure here. Procedure. Procedure is A, find critical points and only keep those in the closed domain. And B is a check f values along edges and the corners. See, and then compare. One note is that when you compare the function value, you also need to compare. You also need to bring in the function value at a critical point to compare that. All right. So this is a fixed procedure for us to find the global or absolute max or min for a function in this closed domain. And there is one more tricky question, which is optimizing f of xy, for example, subject to constraint g of xy equals 0. And we want to use it, we want to solve it by using so-called the Lagrange multiplier method. Okay, so the way of doing it is to introduce this Lagrange function, which is given by little f of xy minus lambda times g of xy. And the equation we need to set up and solve x, y, and the lambda from three things: capital F sub x, partial capital F, partial x equals 0, partial capital F, partial y equals 0, and the partial capital F, partial lambda equals 0. Those three equations are set it up together, and they are translated into partial little f partial x equals lambda times partial little g partial x, partial little f partial y equals lambda times partial little g partial y. And the last equation we should write will be g of xy equals 0. So we solve for x, y, and the lambda, and then we check the function value at those x, y. We can put x star, y star here to indicate that we needed a pair of value for this x and y. All right, so there are quite a bit of calculation we need to do, especially for this, and for all the items in the optimization, it's better to review the notes and then do the homework again, and check your quiz and preparation question for the quiz. and make sure you understand the concept and know how to compute. That's very important. All right. So after this, before this optimization, we were talking about also kind of the chain rule for functional multivariables. um, the for the simple one, um, um, we can have some example. And for example, we're thinking about the polar coordinates. Both x and y are function of r and theta. For example, x equals r times cosine theta, y equals r times sine theta. And then what is partial f partial r equals? Well, the chain rule is partial f partial the first layer of the variable. We can set up the so f is depending on x and y, and each of x and y will be depending on r and theta. Okay, so we are having all those branches starting from f and reach the r. So with this chain of branching structure, when we try to compute a partial f partial x, sorry, partial f partial r, we have to go through from f, go through the x and reach r. And we need also go from f through y and reach r. And then the formulation for the chain rule will be partial f partial x and partial x partial r plus we have two branch in the chain, and then we have the summation partial f partial y times partial y partial r, and so on and so forth. All right, and another check or thing we really do is that from here you can see cosine theta is XOR, and R is what? Because remember, R is indeed square root. R is a square root of x squared plus y squared. So we can represent cosine theta and also sine theta by using x and y on it. So this is some tricks that we sometimes need to solve a problem. All right. And then before the chain rule, we also talk about the so-called the gradient vector and the directional derivative. The directional derivative is indeed a special application of this gradient vector, and we need to know how to compute all those important terms. So for example, if we have f, which depends on two variables, x and y, and then we're going to get the gradient vector for this scalar function, which is a two-dimensional vectors. And the two components of this gradient vector will be the partial derivatives. Okay, so if we have function f depending on three variables x, y, z, and the gradient of the scalar function little f will be having three components. All right, so that's a three-dimensional vectors. Okay, and also the we got to remember the special property of the gradient vector. Okay, so for f of xy at, for example, x0, y0, the direction along which f increase as test is the gradient of f at this point. So this is a property we discussed after the gradient and the directional derivative, right? So also the direction along which f decrease fastest is the negative of gradient. So negative gradient, this is the something that we should comment on in the quiz last week. Okay, because some of you sort of forgot about this property when you are working on this quiz question. All right, and the directional derivative, how do we compute the directional derivative? This is a gradient, and the directional derivative is denoted directional derivative along the direction v for function f(x,y) at the point x0, y0 is obtained by computing the gradient vector of this function f at this point and then dot with this given direction of v and divided by the length of v. So here, if v is indeed a unit vector, then the length of v is just constant 1, then things will be easier. But if not, then we have to figure out the length of v. All right. And in the quiz the week before, not this one we just finished, we do answer the question along the what is directional derivative if we start from one point and move towards the other. That is the second one is not the direction, it is a point given in the quiz question. You have to figure out what is the v, what is the direction we want to compute the directional derivative with by using those 2 points. Okay, so that is the knowledge we went over in the first part of this course. Okay, so now what? Now we want to discuss other topics, which is tangent plane. Okay, so how do we construct the tangent plane for the for 2 things? We have one tangent plane for level surface given by capital F of x, y, z equals 0 at this point A, B, C. All right, the we should know there's a vector, the normal vector to the level surface at the point A, B, C. So here, because we assume this ABC is on this level surface, so what we should know is F capital F of ABC equal 0. Okay, so this gradient, oh sorry, the normal vector of this level surface at the point ABC is indeed the gradient of this capital F at that particular point. All right, so the equation, the level equation of tangent plane, so the equation of tangent plane at the point A, B, C is, then we use this normal vector. I remember this normal vector is indeed partial f partial x at ABC, partial f partial y at ABC, and the partial f partial z at ABC. Okay, so the equation, normal equation is given by the first component of normal vector times the x minus the a partial y at ABC times y minus b plus partial capital F partial z at this point ABC on the level surface multiply b minus c. This is equation of tangent plane for this level surface given by this equation. Okay, and then there's the second type of the normal vector and the tangent plane, which is tangent plane or the graph function. We said we could convert this into the level surface by writing this capital F as a z minus little f, or capital F equals f minus little f minus z. So for those, we have the so-called upward normal to the graph of function at the point x equals to a, y equals b, and z will be certainly not c anymore, or you can name c as little f of ab. Okay, so the normal vector upward normal will be negative partial f partial x, negative partial f partial y, positive 1. So this is upward normal. And we also have the downwards normal. To the graph of function at this point, which will be normal vector. So the only thing different from the upper normal is that we multiplied by -1. Okay. All right. So well, with this normal vector, we can have the equation with the tangent plane now, which is z equals f of AB plus partial f partial x at AB times x minus a plus partial f partial y at AB times y minus b. Okay, so this is also very, very important. Let's just pause for a moment.